So in this video we're just going to do a couple of examples of solving this linear second order uh, homogeneous differential equation with constant coefficients. It's a mouthful. But the idea here is that, what are we doing? Here's our differential equation. Ay double prime plus by prime plus cy equals 0. Here's our ansatz. And in plugging in the ansatz into the differential equation, we ended up with this equation, which is the characteristic equation. Did everybody catch the vocabulary that I'm using there? Let's say that again. So here's a linear homogeneous differential equation with constant coefficients. Homogeneous meaning what? The right hand side is 0. Our ansatz, what does ansatz mean? It means this is kind of our initial guess for a solution. Then we're going to use that guess, we're going to plug that solution into the differential equation and see what happens. Okay, in so doing, we ended up with an equation called the characteristic equation. And notice in particular, right, the relationship between these two things. Right, so this is ay double prime plus by prime plus cy equals 0, and the characteristic equation is ar squared plus br plus c equals 0. Right, so you could just go directly from here to here just by looking to see the a is the constant in front of y prime double prime. That's going to be the constant in front of r squared. B goes in front of y prime in the original. It goes in front of r in the characteristic equation, and c is our constant, and then we set it equal to 0. Good. And of course, once we get to this point, we want to solve that. And so the general way of finding the solution is to use the quadratic formula, but you're not going to use the quadratic formula very often, I hope, because we typically would solve this by using probably factoring if possible, and if it doesn't factor, I would recommend doing completing the square. And so maybe we'll do that first, and then we'll solve a couple of different, let's solve a differential equation first. Let's see. Okay, so we'll solve a differential equation, then we'll talk about completing the square second. So let's solve. Oh gosh, that was terrible penmanship. SOLVE y double prime plus 5y prime plus 6y equals 0. And let's go ahead and put in our initial values as well. Y of 0 equals 1, and y prime of 0 equals 2. And so our initial position is 1, initial velocity is 2. Good. So now we put in our, formally, right, you could use your ansatz. We'll just write down, just as a reminder, whoops. Ansatz, my laptop is trying to update itself, so hopefully it won't do that until I'm finished. So plugging in our ansatz, we get the characteristic equation. Characteristic equation will be r squared plus 5r plus 6. That's easy to factor. Does that do it? 2r, 3r, 5r, 6, good. So r is equal to minus 2 minus 3. Good. So now we have our general solution. The general solution is that y equals c1 e to the r1t minus 2t plus c2 e to the minus 3t. Good. And now we want to plug in our initial conditions. So y of 0 equals 1 will translate to 1 equals c1 e to the 0 plus c2 e to the 0, or 1 is equal to c1 plus c2. Excuse me. And the next one will be y prime of 0 equals 2. So notice when you take the derivatives, I'll do it up here, all that's going to happen, right, is these constants are going to pop out in front. So we'll have minus 2c1 e to the minus 2t minus 3c2 e to the minus 3t. And so when we take our derivative now, y prime of 0 equals 2, we'll have 2 equals minus 2c1 e to the 0 minus 3c2 e to the 0, or 2 is equal to minus 2c1 minus 3c2. Good. What do you see here? This is a system of two equations and two unknowns. How did we solve those? Cramer's rule. Do you have to use Cramer's rule? I would recommend just getting used to it, although you could either substitute or eliminate one of the variables. That's fine. But we would just want to get used to using Cramer's rule. So let's go ahead and do it. So Cramer's rule says that C1. Oh, before I do that, let's go ahead and take the determinant of our coefficient matrix here, minus 2, minus 3. So that's going to be minus 3 minus minus 2. Minus 3 plus 2 is minus 1. Okay. And now, so that's going to be our denominator, right, for C1 and C2. So C1 is equal to, in this case, the 1, negative 2 is replaced by a 1, 2. And then the second column is the same. And then we have our minus 1 that we just computed. And then before we do finish that, let's go ahead and write down C2. That's going to be 1 minus 2 coming from our original. And then in place of 1 minus 3, we'll have a 1 plus 2. Or 1 and a plus 2. And over minus 1. Good. So this looks, going back here now, computing C1, minus 3 minus 2 over minus 1 is equal to 5. 2 minus minus 2 over minus 1 equals minus 4. Very good. So therefore, we have our solution. 5e to the minus 2t minus 4e to the minus 3t. Good. And you'll notice, by the way, that because these are negative, right, both negative in the exponent, y of t goes to 0 as t goes to infinity. It's always good to look at your solution just to kind of get a sense for what happens at large values of time, because that's a common question. Good. Now let's try another exercise that's a little bit different. Let's see if we can go backwards. Example 2. Find a second order linear homogeneous DE whose solution is given by y equals c1 e to the 2t plus c2 e to the minus t. How am I going to do that one? Well, hopefully you see that we're kind of working backwards, right, from where we were last time, not yesterday. I almost said yesterday. The two solutions to the characteristic equation are r equals 2 and r equals minus 1. So therefore, can you figure out what the polynomial is? It's going to be r minus 2 times r plus 1. That will be the characteristic equation, right? So that's going to be r squared minus 2r plus r minus 2, r squared minus r minus 2. Good. And so therefore, what is the differential equation? Y double prime minus y prime minus 2y equals 0. Good. All right. Should we try one more? I think we have time for a short one here. So let y double prime minus y prime minus 2y equals 0. Oh gosh, I need to work on my penmanship here. Y of 0 equals 2. Y prime of 0, I think I drank too much coffee this morning, equals alpha. Okay, we want to first solve, and then we'll see if there's a value of alpha so that all our solutions will go to 0. Find alpha so that y goes to 0 as t goes to infinity. Okay, so let's see what happens here. That's an r squared. Is that really, or gosh, you know, I made this problem up right off the top of my head. I didn't realize we were going to have the same solution. That was tricky. So we end up seeing that we have the same solution as last time. That's odd. So that's r equals minus 1 and 2. And so therefore, I must have had that on my mind here. Let's just to make sure I'm keeping consistent here. I'm going to do 2t first. Okay, good. And now if I plug in my two initial conditions, right, I'm going to get my system of two equations and two unknowns. So 2 is equal to c1 plus c2 is going to be for y of 0, and then for y prime, remember the constants just pop out in front, so that's going to be 2c1 minus c2. Good. Okay, so now at this point you could use Cramer's rule to figure out what the full solution is. If we do that, by the way, you could also just add straight down, right, to eliminate a variable. 3c1 is equal to 2 plus alpha, or alpha plus 2. c1 is alpha plus 2 over 3. And then it turns out that c2 is going to be 4 minus alpha over 3. And so you can all leave, I'm running a little bit short of time, so I'll leave that for you. But so that's our general solution. And so what do we need in order for this function to go to 0 as t goes to infinity? What choices do we have here for c1 and c2? I think you'll agree that c1 should be 0, right? Oops, sorry about that. Oh gosh, I'm making a big mess. c1 needs to be 0, which means alpha plus 2 over 3 equals 0, which means that alpha equals minus 2. There it is. So if I have an initial velocity of -2, my solution will go to 0, and I'm running short of time. I'll see you later.